Hello, my name is Alex Sobotka, and I am a graduate student at UNC Chapel Hill. My research is in cosmology, and specifically, I study what happened in the early universe, so within the first few 100,000 years after the Big Bang. And my project set out to analyze this time period between BBN and recombination. So, what do I mean by that? Well, here's a general timeline of our universe. And there's a lot here, but I want to call your attention to two key events, and those are Big Bang nucleosynthesis, also known as BBN, and recombination. BBN is when the universe had expanded and cooled enough such that nuclei were able to form. And these nuclei fused together to create elements like deuterium and helium. We can actually measure the amount of helium and deuterium out in the universe and use those to infer what happened at BBN by extrapolating backwards. So it turns out we actually know a lot about Big Bang nucleosynthesis. After that, the universe was kind of this soup of nuclei and electrons and photons. And it turns out that the photons couldn't get very far because they kept bouncing off of these electrons. So we had to wait for the universe to expand and cool even more, such that the electrons could combine with the nuclei. This is what we call recombination, 380,000 years after the Big Bang. And now the photons can travel freely, and they travel to us today so that we can observe them as the cosmic microwave background. So we observe this background and we can learn a lot about the time of recombination. So to recap, we know a lot about BBN and we know a lot about recombination, but the time period between these two events can be a little fuzzy. In between, we know that the energy of the universe was dominated by radiation. But other than that, it's not clear if the expansion rate of the universe could have been different compared to our standard picture. So my project set out to quantify how much wiggle room is allowed during this time by our observations of recombination and BBN. Specifically, I set out to test the possibility of a hidden sector particle. It's theorized that dark matter could be part of some hidden or dark sector that doesn't really talk to the visible standard model of particles that we are familiar with. So if this dark matter is its own antiparticle, it could annihilate, and that annihilation could produce a new dark sector particle called the Y particle. That Y particle could then decay into visible sector radiation like photons and neutrinos. So we actually modeled this type of decay, and in order to test whether this type of scenario is allowed by our observations, we used what's called a Markov chain Monte Carlo analysis. The main takeaway from that is this plot here, where on the y-axis, we have a number that just tells us what the Y particle is decaying into. A value of F equals 1 means it's decaying completely into photons, and F equals 0 means it's decaying completely into neutrinos. The value on the x-axis here, you can think of as just how much of the Y particle is there. So when we are only constraining using observations of recombination, you can see that a lot of values are allowed for this x-axis max ratio value. However, when we start including data from Big Bang nucleosynthesis, you can see that the max ratio, that x-axis, gets really constrained. In fact, it gets constrained all the way down to 0.0256. In other words, this is saying that the data tells us that if this Y particle did exist, it was constrained to be at most 2.56% of the energy density of the universe. And while this may not seem to be that significant of a contribution, during our analysis, we actually came to the realization that the presence of this Y particle has implications for how many massive neutrinos there are in the universe. And this is important because currently, cosmology is able to infer a bound on the sum of neutrino masses. And that is a very tight bound. It's very good. At the same time, laboratory experiments here on Earth also have something to say about the bound on the neutrino mass, but it's not as tight as our cosmology inferred bounds. So during the course of our analysis, we realized that this decay had the potential to loosen the cosmology inferred bounds on the neutrino mass by changing the amount of massive neutrinos in the universe. So there's the possibility for this decay scenario to bridge the gap between the two methods and bring the cosmology inferred bound into the realm of direct detection. So that's where we're heading next. And I would like to thank NC Space Grant for funding this research. And I look forward to what's to come.